Welcome to the Whispering Galaxy, where we explore the cosmos, one gentle revelation at a time. I'm delighted you found your way here to this quiet corner of the universe, where we'll embark on journeys that stretch from the smallest whispers of matter to the grandest symphonies of space and time. Tonight, we're setting off on something truly special, a complete cosmic tour that will carry us through every layer of existence, from the quantum dance happening inside your very atoms to the mysterious forces shaping galaxies billions of light years away. Before we begin drifting through the stars together, I'd love to know where you are right now. Are you curled up in bed somewhere in Tokyo as the city sleeps? Perhaps you're watching from a cozy apartment in London while rain taps against the windows. Or maybe you're somewhere under the open sky, where you can actually see the Milky Way stretching overhead like a river of ancient light. Wherever you are, whatever time it is, you're exactly where you need to be for this journey. Now, I should probably warn you, this might be far too fascinating for a proper night's sleep. We're going to wander through some truly mind-bending territory tonight, and there's always the risk that you'll find yourself wide awake at 3 a.m, pondering the mysteries of dark matter, or wondering about parallel universes. But if that happens, well, at least you'll have some extraordinary cosmic company to keep you entertained until dawn. If you enjoy these gentle explorations through the universe, I'd be truly grateful if you'd consider leaving a like or subscribing to this little channel. It helps more fellow cosmic wanderers find their way here. And there's something beautiful about building a community of people who look up at the night sky and feel that same sense of wonder and curiosity. As always, everything we discuss tonight is purely for the joy of learning and relaxation. If you're dealing with any health concerns or persistent sleep troubles, it's always wise to speak with a professional rather than relying on cosmic contemplation alone. So let your shoulders drop, allow your breathing to slow, and prepare to embark on the most comprehensive tour of existence you've ever taken. We're going to start impossibly small and work our way up to the incomprehensibly vast. And along the way, we'll discover that every scale of the universe has its own particular magic, its own secrets, and its own gentle way of reminding us just how extraordinary it is to be conscious observers in this cosmic dance. Picture, if you will, the smallest possible realm of existence. We're diving deep into the quantum world, that strange and beautiful foundation upon which everything else is built. Down here, reality operates by rules so different from our everyday experience that even the most brilliant physicists admit they don't fully understand what's happening. They've simply learned to work with the mystery. In this quantum realm, particles aren't really particles in the way you might imagine. They're not tiny marbles bouncing around in empty space. Instead, they're more like ripples in invisible oceans, fields of pure potential that fill every corner of existence. When these fields get excited, when they vibrate in just the right way, particles appear. It's as if the universe is a vast instrument, and particles are the notes that emerge when its strings are plucked by forces we're only beginning to understand. Take the electron, that fundamental building block of matter. It exists as a disturbance in what electron field, and physicists call the invisible presence that permeates all of space and time. When this field gets sufficiently excited, an electron materializes, carrying its tiny charge and spinning in ways that don't quite correspond to anything in our macro world. These electrons dance around atomic nuclei, creating the chemistry that makes life possible, the electricity that powers our cities, and the neural activity that allows you to contemplate these very words. Then there are photons, those weightless messengers of light that connect every corner of the universe. They emerge from disturbances in the electromagnetic field, carrying energy and information across impossible distances without ever aging or slowing down. A photon born in the heart of a distant star experiences no passage of time on its billion-year journey to your eyes. From its perspective, it leaves the star and arrives at your retina in the same eternal instant. The quantum world operates on probability rather than certainty. Before you measure a particle's position, it exists in a cloud of possibilities, spread out across space like a gentle fog of potential. Only when you look, when you interact with it in some way, does it collapse into a definite location. It's as if reality is constantly improvising, making decisions about what's real only when pressed for an answer. This leads to one of the most beautiful and bewildering aspects of quantum mechanics: superposition. A quantum particle can exist in multiple states simultaneously until the moment of observation. It's not that we simply don't know which state it's in. It genuinely exists in all possible states at once. This isn't just theoretical poetry. It's been demonstrated in countless experiments and forms the basis for emerging technologies like quantum computers. Even stranger is quantum entanglement, where two particles become so fundamentally connected that measuring one instantly affects the other, no matter how far apart they are. Einstein called this spooky action at a distance, and while it troubled him deeply, modern experiments have confirmed it repeatedly. These entangled particles share a kind of cosmic intimacy that transcends space and time, remaining connected across the entire breadth of the universe. What's perhaps most remarkable about the quantum realm is that it's not some exotic corner of reality that only affects particle accelerators and advanced physics labs. It's happening right now, inside your body, powering the chemical reactions that keep you alive. Every breath you take, every thought you think, every beat of your heart depends on quantum processes unfolding in your cells. You are, quite literally, a walking quantum phenomenon. The uncertainty principle tells us that, at the deepest level, nature is fundamentally fuzzy. You cannot simultaneously know both the exact position and momentum of a particle. The more precisely you pin down one property, the more uncertain the other becomes. This isn't a limitation of our measuring instruments. It's a feature of reality itself. The universe seems to have a built-in resistance to being completely figured out. Virtual particles constantly pop into and out of existence in the quantum vacuum, borrowing energy from empty space for the briefest instants before disappearing again. This isn't empty space being truly empty. It's a seething ocean of possibility, constantly bubbling with potential. These fleeting visitors have measurable effects on the properties of matter, influencing everything from the behavior of atoms to the structure of molecules. As we begin to scale up from this quantum foundation, we encounter the first stable structures that emerge from this chaos of possibility: atoms. These are the first real citizens of the universe, the basic building blocks from which everything else is constructed. Each atom is like a tiny solar system, with a dense nucleus at the center surrounded by clouds of electrons. But unlike planets orbiting the sun, these electrons exist in probability clouds, regions where they're likely to be found rather than specific paths they follow. The nucleus itself is a marvel of cosmic engineering, packed with protons and neutrons held together by the strong nuclear force against the electromagnetic repulsion trying to tear them apart. This is where the universe stores most of its mass, compressed into a space so small that if atoms were scaled up to the size of football stadiums, their nuclei would still be smaller than marbles. Different combinations of protons, neutrons, and electrons create the 100+ elements that make up the periodic table, each with its own personality and behavior. Hydrogen, the simplest and most abundant, consists of just one proton and one electron. Carbon, the basis of all organic chemistry, has 6 of each. Gold, that symbol of value and beauty, requires 79 protons in its nucleus. What's truly magical is how these atoms, following simple rules of attraction and repulsion, combine to create molecules of staggering complexity. Water, that essential compound for life, emerges when 2 hydrogen atoms share their electrons with 1 oxygen atom. The result is something with entirely new properties, a substance that can exist as ice, liquid, or vapor, that can dissolve countless other compounds, and that makes possible the intricate chemistry of living things. As we continue our cosmic tour, ascending from atoms to molecules to the first stirrings of chemistry, we begin to see how the universe builds complexity from simplicity. Each level of organization follows naturally from the one below, yet each reveals new properties and possibilities that weren't apparent at smaller scales. This is the first glimpse of how the cosmos creates beauty and meaning from the quantum dance of possibility, building a universe rich enough to contain stars, planets, and conscious beings capable of wondering about their own existence. Chemistry is where atoms discover they don't have to be alone. It's the universe's first social network, where individual elements reach out to form bonds, create partnerships, and build something larger than themselves. When atoms come together, they don't just sit quietly next to each other. They share, they give, they take, and in doing so, they create entirely new identities with properties that would have been impossible to predict from their individual parts. Consider salt, that most familiar of compounds. Take sodium, a metal so reactive it explodes when it touches water. And chlorine, a toxic green gas that was once used as a weapon of war. Individually, both are dangerous, unstable, eager to react. But when they meet, when that single electron from sodium finds its way to chlorine's outer shell, something remarkable happens. They become sodium chloride, stable, crystalline, and essential for life. The dangerous becomes benign, the reactive becomes calm, and together they create something that enhances the flavor of our food and regulates the chemistry of our bodies. This is the magic of ionic bonding, where atoms achieve stability by transferring electrons completely, but chemistry has other tricks up its sleeve. In covalent bonding, atoms choose to share rather than give or take. Water emerges from this kind of cooperation. Two hydrogen atoms sharing electrons with oxygen, creating a molecule with a slight positive charge on one end and a slight negative charge on the other. This polarity gives water its remarkable properties, its ability to dissolve so many substances, its tendency to form hydrogen bonds with other water molecules, and its unique behavior of expanding when it freezes. Carbon deserves special mention in our chemical story. If atoms were actors, carbon would be the versatile star capable of playing any role. With 4 electrons available for bonding, carbon can connect to 4 other atoms, creating an almost infinite variety of structures. It can form chains that stretch for thousands of atoms, rings that create the foundation of aromatic compounds and 3-dimensional frameworks of stunning complexity. Carbon is the basis of organic chemistry, the chemistry of life, because it's so willing to form stable bonds with itself and with other elements. The dance of chemistry extends far beyond individual molecules. When we scale up to collections of molecules, we encounter new phenomena entirely. Phase transitions occur when molecular motion overwhelms or succumbs to intermolecular forces. Ice melts when thermal energy gives water molecules enough motion to break free from their rigid, crystalline structure. Steam condenses when molecules slow down enough for their attractive forces to pull them together into liquid droplets. These transitions reveal how temperature, really just the average kinetic energy of molecules, can dramatically alter the behavior of matter. Chemical reactions are like cosmic conversations between molecules, exchanges that can be gentle or explosive, slow or instantaneous. When wood burns, cellulose molecules react with oxygen from the air, breaking old bonds and forming new ones, releasing energy that once came from sunlight captured by growing trees. Photosynthesis runs this reaction in reverse, using sunlight to build complex sugar molecules from simple carbon dioxide and water, storing solar energy in chemical bonds that can be released later. The chemistry happening in your body right now is staggeringly complex. Proteins fold into precise three-dimensional shapes that allow them to catalyze specific reactions, speed up processes that would otherwise take millions of years. DNA molecules store information in sequences of 4 simple bases, creating a code that contains the instructions for building and maintaining an entire organism. Enzymes work like molecular machines, grabbing specific molecules, holding them in just the right orientation, and facilitating reactions with extraordinary precision. But chemistry isn't confined to laboratories and living things. It's happening everywhere in the universe. In the cores of stars, nuclear fusion creates heavier elements from lighter ones, following the fundamental rule that atoms seek more stable configurations. When massive stars explode as supernova, they scatter these newly formed elements across space, seeding future generations of stars and planets with the raw materials for complex chemistry. In the vast molecular clouds that drift between stars, simple molecules form despite the cold and vacuum of space. Water, ammonia, and methanol have all been detected in these cosmic nurseries, along with more complex organic compounds that hint at the chemical richness possible even in the most seemingly barren environments. These molecules serve as cooling agents, helping gas clouds collapse under their own gravity to form new stars and planetary systems, on shapes, landscapes, and atmospheres. Venus planets throughout the universe, chemistry's thick carbon dioxide atmosphere creates a runaway greenhouse effect, while Mars's thin atmosphere allows water to exist only as ice or vapor. Titan, Saturn's largest moon, has lakes and rivers of liquid methane and ethane, hydrocarbons that exist as gases on Earth but remain liquid in Titan's frigid environment. Each world's chemistry tells a unique story of temperature, pressure, and the availability of different elements. The transition from chemistry to biology represents one of the most profound leaps in cosmic complexity. Somewhere, somehow, collections of molecules began to organize themselves in ways that could maintain their structure, respond to their environment, and even reproduce. This emergence of life from chemistry remains one of the greatest mysteries in science, but we can see hints of how it might have happened. Lipid molecules naturally form membranes that can enclose other molecules, creating the first cellular boundaries. RNA molecules can both store information and catalyze chemical reactions, suggesting they might have been among the first self-replicating systems. Amino acids, the building blocks of proteins, form readily under conditions that likely existed on the early Earth. While we don't yet know exactly how these pieces came together to create the first living systems, chemistry provides all the necessary components. What's remarkable is how chemistry manages to create such incredible diversity from relatively simple rules. The periodic table contains fewer than 120 elements, yet these can combine in countless ways to produce millions of different compounds. Each combination follows the same basic principles: atoms seeking stable electron configurations, charges balancing, energy minimizing. Yet the results range from the simple elegance of water to the mind-boggling complexity of DNA. As we prepare to scale up from molecules to the larger structures they create, it's worth pausing to appreciate this chemical realm. Every flavor you taste, every color you see, every scent that triggers a memory, all of these sensations arise from molecules interacting with receptors in your body. The chemistry of neurotransmitters allows your brain to process thoughts and emotions. The chemistry of hormones regulates everything from growth to sleep cycles to the experience of love. Chemistry is the universe learning to build with purpose, creating structures that can store information, harness energy, and respond to change. It's the bridge between the quantum randomness of individual particles and the organized complexity of living systems. In the grand cosmic story, chemistry represents the moment when matter began to discover its own creative potential, setting the stage for the emergence of biology and, ultimately, consciousness itself. From this rich chemical foundation, we're ready to explore how these molecular interactions scale up, to create the larger structures and forces that shape our cosmic neighborhood. The same principles that govern how atoms bond and molecules interact will guide us as we venture into the realm where chemistry gives way to physics, where individual reactions become collective behaviors, and where the stage is set for the grand theatre of stars, planets, and the forces that bind them all together. As we emerge from the intimate world of molecular bonds and chemical reactions, we find ourselves at the threshold of something magnificent, the realm where individual forces begin to orchestrate the grand symphony of the cosmos. Here, in this middle territory between the molecular and the astronomical, we encounter the fundamental forces that shape everything from the gentle fall of autumn leaves to the violent dance of colliding galaxies. Imagine for a moment that you could step outside of your everyday experience and observe the invisible threads that hold the universe together. You'd see a tapestry woven from 4 fundamental forces, each playing its own essential role in the cosmic ballet. These forces don't work in isolation. They collaborate, compete, and combine to create the rich complexity of the world around us. The first force we encounter is perhaps the most familiar: gravity. It's the gentle pull that keeps your feet on the ground, the invisible hand that guides the moon in its monthly journey around Earth, and the cosmic architect that shapes the largest structures in the universe. Gravity seems deceptively simple. Mass attracts mass, and the more massive something is, the stronger its gravitational pull. Yet this apparent simplicity conceals profound mysteries. Einstein revealed that gravity isn't really a force in the traditional sense. Instead, it's the curvature of space and time itself. Imagine the universe as a vast, flexible fabric. When you place a massive object like a star or planet on this fabric, it creates a depression, a warping of the material. Other objects rolling across this fabric naturally follow the curves, creating what we experience as gravitational attraction. This elegant geometric interpretation explains not just why apples fall from trees, but why light bends around massive objects and why time itself runs more slowly in strong gravitational fields. The electromagnetic force operates on an entirely different principle, but with equally profound consequences. This is the force responsible for the aurora dancing across polar skies, the lightning that illuminates thunderstorms, and the gentle warmth of sunlight on your skin. At its heart, electromagnetism governs the behavior of charged particles: protons with their positive charge, electrons with their negative charge, and the intricate ways they interact across space. Unlike gravity, which only attracts, electromagnetism can both attract and repel. Opposite charges draw together while like charges push apart, creating a dynamic tension that shapes the structure of atoms, powers the chemistry we've just explored, and generates the electromagnetic waves that carry information across the cosmos. Every radio signal, every beam of visible light, every X-ray from a distant star is an electromagnetic wave rippling through the fabric of space. The electromagnetic force is also responsible for most of the phenomena we encounter in daily life. When you touch a surface, you're not actually making contact at the atomic level. Instead, the electromagnetic fields around the electrons in your fingers repel the electromagnetic fields around the electrons in the surface, creating the sensation of solidity. The colors you see result from atoms absorbing and emitting specific frequencies of electromagnetic radiation. Even the very stability of matter depends on the delicate balance between electromagnetic repulsion and the attractive forces that hold atomic nuclei together. This brings us to the strong nuclear force, the cosmic glue that binds protons and neutrons within atomic nuclei. This force operates only at incredibly short ranges, distances smaller than the nucleus of an atom, but within that tiny realm, it's the most powerful force in the universe. Without it, The electromagnetic repulsion between positively charged protons would instantly tear apart every atomic nucleus, and matter as we know it simply couldn't exist. The strong force has a curious property. Unlike gravity or electromagnetism, which weaken with distance, the strong force actually becomes stronger when you try to pull quarks apart. It's like having a rubber band that gets stiffer the more you stretch it. This explains why quarks are never found in isolation. They're always bound together in groups of 2 or 3, forming the protons and neutrons that populate atomic nuclei. The fourth fundamental force, the weak nuclear force, might seem like the quiet sibling in this cosmic family, but it plays a crucial role in the story of the universe. This force governs certain types of radioactive decay and is essential for the nuclear fusion processes that power stars. Without the weak force, the sun couldn't convert hydrogen into helium, and the steady stream of energy that makes life possible on Earth would never have begun. These 4 forces work together to create the hierarchical structure of the universe. The strong force binds quarks into protons and neutrons. The electromagnetic force holds electrons in orbit around nuclei, creating atoms. Chemical bonds, themselves electromagnetic in nature, link atoms into molecules. Gravity assembles these molecular collections into planets, stars, and galaxies. Each level of organization emerges from the level below, yet each displays properties and behaviors that couldn't have been predicted from studying the smaller scales alone. Consider how these forces shape the life cycle of a star. Gravity pulls together vast clouds of gas and dust, compressing them until temperatures and pressures become extreme enough for nuclear fusion to begin. In the star's core, the strong force enables hydrogen nuclei to overcome their electromagnetic repulsion and fuse together, releasing the energy that makes stars shine. The weak force facilitates some of these nuclear reactions, while electromagnetic radiation carries energy from the core to the surface and then out into space. For billions of years, these forces exist in a delicate balance. Gravity tries to collapse the star, while the outward pressure from nuclear fusion pushes back. Eventually, when the fuel runs out, gravity wins. For smaller stars, this leads to a gentle expansion into a red giant followed by the formation of a white dwarf. For larger stars, the collapse is catastrophic, resulting in a supernova explosion that can outshine an entire galaxy for weeks. These stellar explosions are cosmic recycling centers, scattering heavy elements forged in stellar cores across space. The carbon in your body, the oxygen you breathe, the iron in your blood, all of these elements were created in the nuclear furnaces of ancient stars and distributed through space by supernova explosions. In a very real sense, you are made of recycled starlight, assembled from atoms that have been on an incredible journey through space and time. The interplay of forces extends beyond individual stars to shape the structure of galaxies themselves. Gravity pulls matter together into dense clusters, but the rotation of these clusters creates centrifugal forces that prevent complete collapse. The result is the elegant spiral structure we see in galaxies like our own Milky Way, with arms of stars and gas sweeping outward from a central bulge. Dark matter, that mysterious substance that makes up most of the matter in the universe, reveals itself primarily through its gravitational effects. We can't see it directly because it doesn't interact electromagnetically. It doesn't absorb, emit, or reflect light. But its gravitational influence is unmistakable, affecting the rotation of galaxies, the bending of light from distant objects, and the large-scale structure of the universe itself. On the larger scales, the universe is shaped by the ongoing competition between gravity and a mysterious force called dark energy. While gravity tries to pull everything together, dark energy appears to be pushing space itself apart, causing the expansion of the universe to accelerate. This cosmic tug-of-war will ultimately determine the fate of everything, whether the universe will continue expanding forever, eventually collapse back in on itself, or reach some other destiny we haven't yet imagined. Even the passage of time itself is influenced by these fundamental forces. Einstein showed us that time runs more slowly in strong gravitational fields and for objects moving at high speeds. This isn't just theoretical. GPS satellites have to account for these effects to maintain their accuracy. The time dilation near a black hole can be so extreme that an outside observer would see someone falling toward the event horizon appear to slow down and freeze at the boundary, while from the falling person's perspective, they would cross the horizon and continue toward the center in normal time. The forces we've explored operate across an incredible range of scales, from the subatomic realm where the strong force binds quarks, to the cosmic scale where gravity sculpts the largest structures in the universe. They work in harmony to create the conditions for life and ultimately necessary for complexity, for chemistry, for consciousness. Without the precise balance between these forces, stars couldn't form, atoms would be unstable, and the rich tapestry of cosmic evolution would never have unfolded. As we prepare to venture outward from this foundational understanding of forces, we're ready to explore how they manifest in the cosmic structures that surround us. The stars that illuminate the night sky, the planets that orbit them, and the vast galactic neighborhoods that stretch across billions of light years. Each of these cosmic citizens owes its existence to the intricate dance of fundamental forces, and each tells a unique story about how the universe transforms energy and matter into the breathtaking complexity we observe today. Now, as we drift outward from the realm of fundamental forces, we find ourselves approaching the first major landmarks of our cosmic journey, the stars themselves. These brilliant beacons scattered across the night sky aren't just distant points of light. They're magnificent nuclear furnaces, cosmic alchemists that spend millions or billions of years transforming the simplest elements into increasingly complex ones, seeding the universe with the very ingredients that make planets, life, and consciousness possible. To truly appreciate stars, we need to understand that they represent one of nature's most elegant solutions to a cosmic problem. Throughout the universe, vast clouds of gas drift through space, mostly composed of hydrogen left over from the early moments after the Big Bang. These clouds are cold, dark, and seemingly lifeless, but gravity never sleeps. Slowly, imperceptibly at first, gravity begins to gather these wispy materials together, creating regions of slightly higher density that attract even more matter. This process continues for millions of years, with the cloud gradually contracting under its own weight. As it shrinks, the gas heats up, the same principle that makes a bicycle pump warm when you compress air. Eventually, the temperature at the center reaches about 10 million degrees Celsius, and something magical happens. The hydrogen nuclei, which have been desperately trying to avoid each other due to their mutual electromagnetic repulsion, finally get squeezed close enough for the strong nuclear force to take over. Nuclear fusion begins, and a star is born. This isn't a gentle process. It's like lighting a controlled thermonuclear explosion that will continue for billions of years. The energy released by fusion creates an outward pressure that perfectly balances the inward pull of gravity, establishing the delicate equilibrium that will define the star's entire adult life. It's a cosmic balancing act so precise that even tiny changes in either direction would cause the star to either collapse or explode. Different stars lead dramatically different lives, and their stories are written in their mass. The smallest stars, called red dwarfs, are the marathon runners of the cosmos. They burn their hydrogen fuel so slowly and efficiently that they can continue shining for trillions of years, far longer than the universe has even existed. These stellar minimalists are incredibly common, making up about 3/4 of all stars, yet they're so dim that we can't see any of them with the naked eye. Our sun represents the middle class of stellar society. It's been fusing hydrogen into helium for about 4.5 billion years, and it has roughly another 5 billion years of steady burning ahead of it. Every second, The Sun converts about 600 million tons of hydrogen into helium, and in the process, it loses about 4 million tons of mass that gets converted directly into energy, according to Einstein's famous equation. This energy travels from the Sun's core to its surface, a journey that takes tens of thousands of years, as photons bounce randomly through the dense solar interior, before finally escaping into space. But the real cosmic drama belongs to the massive stars, those giants with 8 times the mass of the Sun or more. These stellar titans live fast and die young, burning through their nuclear fuel at such a prodigious rate that they might last only a few million years. As they age, they become cosmic onions, with layers of different fusion reactions creating increasingly heavy elements. First hydrogen fuses to helium, then helium to carbon, carbon to oxygen, and so on, all the way up to iron. Iron represents a cosmic dead end. Fusing lighter elements releases energy, which is what keeps stars shining. But iron is at the bottom of the nuclear energy valley. Fusing iron or splitting it, both require energy rather than releasing it. When a massive star builds up an iron core, it's essentially writing its own death warrant. The core can no longer support itself against gravity, and what happens next is one of the most violent events in the universe. The core collapses in less than a second, crushing matter to densities beyond imagination. The rebound from this collapse sends a shockwave racing outward through the star, creating temperatures so extreme that elements heavier than iron can finally be forged. Gold, platinum, uranium, these precious and radioactive elements are created only in the final moments of a star's life, in the cosmic fires of a supernova explosion. The explosion itself is spectacular beyond description. For weeks or months, a single dying star can outshine the combined light of 100 billion normal stars. The blast wave races outward at thousands of kilometers per second, carrying with it all the elements the star created during its lifetime. This stellar material, enriched with heavy elements, mixes with the surrounding interstellar medium, seeding future generations of stars and planets with the chemical complexity necessary for rocky worlds and organic chemistry. What remains after a supernova depends on the original mass of the star. For stars between about 8 and 25 times the mass of the Sun, the collapsed core becomes a neutron star, a city-sized sphere so dense that a teaspoon of its material would weigh as much as Mount Everest. These cosmic lighthouses spin rapidly, often hundreds of times per second, sweeping beams of radiation across space like celestial searchlights. When these beams happen to point toward Earth, we detect them as pulsars, cosmic clocks so precise they rival our best atomic timepieces. For the most massive stars, even neutron matter cannot withstand the crushing force of gravity. The core collapses all the way down to a point of infinite density, a singularity surrounded by an event horizon from which nothing, not even light, can escape. A black hole is born, creating a region of space so warped that the normal rules of physics break down completely. These stellar death throes might seem destructive, but they're actually essential acts of cosmic creativity. Without supernovae, the universe would contain only hydrogen and helium. There would be no carbon for organic molecules, no oxygen for water, no silicon for rocky planets, no iron for planetary cores that generate protective magnetic fields. Every atom in your body, heavier than hydrogen, was forged in the nuclear furnace of a star, or created in the explosive moment of its death. You are quite literally made of ancient starlight, recycled and reformed into something capable of contemplating its own cosmic origins. But stars don't just create heavy elements, they also organize the universe on larger scales. Stellar winds and radiation pressure blow away surrounding gas, carving out bubbles in the interstellar medium. Multiple massive stars in the same region can create superbubbles hundreds of light years across, shaping the structure of entire galactic neighborhoods. When these stars eventually explode as supernovae, they can trigger the formation of new stars by compressing nearby gas clouds. creating a kind of stellar reproduction that spreads across space and time. The light from stars also serves as the universe's communication system, carrying information across vast distances about temperature, composition, motion, and magnetic fields. By analyzing the spectrum of starlight, the precise colors of light each star emits, astronomers can determine what elements are present in stellar atmospheres, how fast stars are moving toward or away from us, and even detect the gravitational influence of orbiting planets. Some stars exist in binary or multiple systems, locked in gravitational dances that can last for billions of years. In these stellar partnerships, we see some of the universe's most dramatic phenomena. When a white dwarf star slowly accretes matter from a companion, it can trigger periodic nova explosions. When two neutron stars spiral into each other, they create gravitational waves that ripple across the fabric of spacetime itself, carrying news of the collision to detectors on distant worlds. Variable stars pulse and flicker in regular patterns, their brightness changing as they expand and contract in response to the changing balance between gravity and radiation pressure. Some of these stellar heartbeats are so regular that they serve as cosmic standard candles, allowing astronomers to measure distances across the universe and discover that space itself is expanding. As we survey this stellar landscape, we begin to see how stars serve as the universe's engines of change and complexity. They gather the raw materials left over from the Big Bang and spend millions or billions of years processing them into increasingly sophisticated forms. They provide the energy that drives planetary weather systems and makes life possible. They create the heavy elements that allow for rich chemistry and solid surfaces. And when they die, they distribute their accumulated wealth across the cosmos, ensuring that each new generation of stars is born into a universe slightly more complex than the one before. The night sky above us is really a vast stellar nursery, factory, and cemetery all at once. Some of the stars we see are still in their stellar infancy, recently ignited and beginning their long journey of nuclear burning. Others are middle-aged, like our Sun, steadily converting hydrogen to helium in their cores. Still others are ancient giants or white dwarfs, representing the endpoints of stellar evolution. And scattered among the visible stars are the invisible remnants, neutron stars and black holes that mark the spots where once brilliant suns have completed their cosmic transformation. This stellar community exists within an even grander structure, one that we're now ready to explore as we continue our cosmic tour. The stars don't drift randomly through space, but instead organize themselves into vast rotating islands called galaxies, cosmic cities containing hundreds of billions of stellar citizens. Our own Milky Way galaxy stretches across 100,000 light-years, and it's just one of countless such structures scattered across the observable universe. As we prepare to scale up from individual stars to these galactic metropolises, we carry with us an appreciation for the stellar processes that make everything else possible. The carbon in our bodies, the oxygen we breathe, the silicon in the earth beneath our feet, all of it was forged in stellar cores and distributed by stellar death. We are not separate from the stars. We are their descendants, temporary arrangements of stellar ash that have somehow learned to wonder about their own origins and gaze back at the cosmic furnaces that gave them birth. Our cosmic journey now carries us beyond the realm of individual stars to witness how these stellar citizens organize themselves into vast, rotating cities of light. Galaxies. These magnificent structures represent one of the universe's most breathtaking achievements in architecture, bringing together hundreds of billions of stars into coherent, dynamic communities that span distances so vast they challenge our ability to comprehend them. Picture, if you will, standing at the edge of our own galactic neighborhood on a perfectly clear night, far from any city lights. That faint, luminous river stretching across the sky, the Milky Way, represents our view from inside one of these cosmic metropolises. We're looking edge-on through the disk of our own galaxy, seeing the combined light of countless distant suns creating that ethereal glow that has inspired countless generations of stargazers and storytellers. The Milky Way is what astronomers call a barred spiral galaxy, and it's a structure of elegant complexity. At its heart lies a central bulge, a dense concentration of older reddish stars surrounding what we now know is a supermassive black hole containing the mass of about 4 million suns. This central giant, called Sagittarius A star, sits quietly at our galaxy's gravitational center, influencing the orbits of nearby stars but remaining invisible to our eyes, detectable only through its gravitational effects on the stellar traffic swirling around it. From this central hub, two major spiral arms sweep outward like cosmic pinwheels, traced by the blue-white light of young massive stars and the reddish glow of stellar nurseries where new suns are still being born. These arms aren't fixed structures like the spokes of a wheel, but rather density waves that move through the galactic disk, regions where matter becomes compressed and star formation is triggered. Our own solar system rides between two of these major arms, in what's sometimes called the local arm or Orion spur. The scale of our galaxy is almost impossible to grasp. Light, traveling at its maximum speed of 300,000 kilometers per second, takes 100,000 years to cross from one edge of the Milky Way to the other. If you could shrink our entire solar system down to the size of a quarter, our galaxy would still stretch across the entire North American continent. We orbit the galactic center once every 225 million years or so, a period astronomers sometimes call a cosmic year. Since Earth formed, we've completed only about 20 of these vast orbital journeys. But galaxies come in many different forms, each telling its own story about cosmic evolution. Spiral galaxies like ours are perhaps the most photogenic, with their graceful arms and active star-forming regions creating some of the most beautiful images in astronomy. The spirals range from tightly wound systems, where the arms make several complete loops, to more open configurations, where the arms sweep outward in gentle curves. Elliptical galaxies represent a different approach to galactic organization. These systems appear as smooth, featureless ovals of light, lacking the spiral structure and active star formation that characterizes their more flamboyant cousins. Ellipticals tend to be dominated by older, redder stars and contain relatively little of the gas and dust needed to form new stellar generations. They're like cosmic retirement communities, places where the stellar population has aged gracefully and settled into a quiet, stable existence. Then there are the irregular galaxies, the cosmic rebels that refuse to conform to any clear pattern. These systems often appear chaotic and asymmetrical, sometimes bearing the scars of gravitational interactions with neighboring galaxies or the disruptive effects of intense star formation. The Magellanic Clouds, our galaxy's closest neighbors, fall into this category, small, irregularly shaped systems that orbit the Milky Way and are slowly being distorted by our galaxy's gravitational influence. The spaces between stars within galaxies are not empty, but filled with a thin interstellar medium composed of gas and dust. This material, though incredibly rarefied by earthly standards, plays a crucial role in galactic ecology. It serves as the raw material for new star formation, gets enriched by stellar winds and supernova explosions, and helps transport heavy elements throughout the galactic system. The dust particles, though tiny, scatter and absorb starlight, creating the dark lanes visible in edge-on spiral galaxies and giving nebulae their distinctive colors and patterns. Galaxies are not solitary objects drifting alone through space, but exist within a vast cosmic web of structure. Our own Milky Way is part of what astronomers call the local group, a gravitationally bound collection of more than 50 galaxies, dominated by ourselves and our larger neighbor, the Andromeda Galaxy. Andromeda, also known as M31, is currently approaching us at about 110 kilometers per second, and in approximately 4 billion years, these two spiral giants will begin a slow-motion collision that will reshape both systems. This impending galactic merger might sound catastrophic, but it's actually a relatively gentle process on cosmic scales. The vast distances between individual stars mean that direct stellar collisions will be extremely rare. Instead, the gravitational interactions will trigger bursts of star formation, distort the spiral arms, and eventually merge the two systems into a single, larger, elliptical galaxy that some astronomers have already nicknamed Milkomeda. The local group itself is just a small part of the Virgo supercluster, which contains thousands of galaxies spread across a region more than 100 million light-years in diameter. And even this enormous structure is just one node in the cosmic web, a vast network of galaxy clusters and filaments that stretches across the observable universe. Between these filaments lie enormous voids, regions of space containing relatively few galaxies, creating a foam-like structure on the largest scales. At the centers of most large galaxies lurk supermassive black holes, gravitational monsters containing millions or billions of times the mass of our Sun. These central engines can have dramatic effects on their host galaxies, regulating star formation and occasionally producing spectacular displays when matter falls toward the black hole. As gas spirals inward, it heats up and glows brightly, sometimes outshining the entire rest of the galaxy. These active galactic nuclei, including objects called quasars, can be detected across billions of light-years, serving as beacons that illuminate the early history of the universe. The relationship between supermassive black holes and their host galaxies appears to be intimate and complex. Galaxies and their central black holes seem to grow together, with the mass of the black hole closely correlated with properties of the galaxy's central bulge. This suggests a deep connection between the growth of these gravitational giants and the evolution of galactic structure itself. Galaxy formation remains one of the active frontiers in cosmology. We understand that galaxies began as small fluctuations in the density of matter in the early universe, regions that were slightly denser than their surroundings and therefore able to grow through gravitational attraction. Over billions of years, these initial seed fluctuations gathered more and more matter, eventually becoming the magnificent spiral and elliptical systems we observe today. But galaxies are not static structures frozen in time. They continue to evolve through a variety of processes. Small galaxies can be captured and absorbed by larger ones, adding their stars to the growing system. Galaxies can collide and merge, triggering bursts of star formation and reshaping their morphologies. Galactic winds driven by supernovae and stellar radiation can blow gas out of smaller systems, while larger galaxies can accrete fresh material from their surroundings. The colors of galaxies tell stories about their stellar populations and recent history. Blue galaxies are dominated by young, hot stars and active star formation, while red galaxies contain mostly older, cooler stars and little ongoing stellar birth. The transition from blue to red often marks a significant event in a galaxy's life, such as the exhaustion of its gas supply or a major merger that disrupts star-forming regions. Modern surveys have revealed that galaxies exist in an incredible variety of forms, from dwarf systems containing only a few million stars to giant ellipticals hosting more than 1 trillion stellar citizens. Some galaxies are smooth and featureless, while others display intricate structures including rings, bars, tidal tails, and other features that record their dynamical histories. The study of distant galaxies allows us to observe cosmic evolution directly. Because light takes time to travel across space, when we look at very distant galaxies, we're seeing them as they were billions of years ago, when the universe was younger and different. These observations reveal that early galaxies were generally smaller, more irregular, and more actively forming stars than their modern counterparts, providing crucial insights into how cosmic structure has evolved over time. Dark matter plays a crucial role in galaxy formation and evolution, providing the gravitational scaffolding that allows normal matter to collect and form stars. Computer simulations suggest that galaxies form within vast halos of dark matter, invisible structures that extend far beyond the visible edges of galactic disks. The distribution of dark matter influences everything from the rotation speeds of spiral arms to the orbits of satellite galaxies. As we contemplate these galactic metropolises, we begin to appreciate the incredible journey that has brought matter from the smooth, nearly featureless universe of the early cosmos to these complex, structured systems filled with billions of individual stars. Galaxies represent one of the universe's greatest achievements in organization, bringing together the products of stellar nucleosynthesis and gravitational assembly into coherent structures that persist for billions of years. Yet even these magnificent galactic cities are just components of something even grander. As we prepare to expand our view beyond individual galaxies to the larger structures in the universe, we're about to encounter phenomena that operate on scales so vast they make entire galaxies appear as mere points of light. The cosmic web, dark matter, dark energy, and the overall geometry and fate of the universe itself await our exploration as we continue this gentle tour through the hierarchy of cosmic organization. Our journey has carried us from the quantum foam of virtual particles to the majestic spiral arms of galaxies, and each step has revealed new layers of complexity and beauty. The universe, it seems, is not content with simple structures, but delights in building elaborate architectures that span every conceivable scale. And we're only just beginning to glimpse the full grandeur of this cosmic construction project. As we drift outward from the galactic neighborhoods we've been exploring, we encounter something truly extraordinary: the discovery that our universe is not the static, unchanging realm that astronomers once imagined, but rather a dynamic, expanding tapestry that continues to grow larger with each passing moment. This revelation, first glimpsed in the early 20th century, fundamentally transformed our understanding of cosmic history and opened our eyes to the possibility that space itself might be alive with motion. The story begins with the realization that galaxies are not simply scattered randomly throughout space, but are actually racing away from us in all directions. The more distant a galaxy appears, the faster it seems to be retreating, as if the entire universe is participating in some vast, coordinated exodus. But this isn't because galaxies are fleeing from our particular cosmic neighborhood. Rather, it's because the fabric of space itself is stretching, carrying these island universes along like leaves floating on the surface of an expanding pond. This cosmic expansion reveals something profound about the nature of space and time. Space isn't simply an empty stage where cosmic events unfold, but rather an active participant in the drama, capable of growth and change. When we say the universe is expanding, we don't mean that galaxies are flying outward through a pre-existing void, but rather that new space is constantly being created between existing structures, increasing the distances between them in a process that affects the entire cosmic landscape. And so our cosmic tour draws to a gentle close, having carried us from the quantum whispers of possibility to the grand symphony of expanding space. We've witnessed how the universe builds complexity from simplicity, layer upon layer, each scale revealing new wonders and deeper mysteries. Whether you've drifted off somewhere between stellar nurseries and galactic neighborhoods, or found yourself wide awake contemplating the nature of reality itself, you've spent this time connected to the greatest story ever told, the story of everything, including you. Rest well, and remember that you are not separate from this cosmic dance, but an integral part of its unfolding beauty.